molecular and nanoscale communications, computing. So we have heard these interesting talks, and now we will try to collect some input about what is the current state. So if you want, you can already answer all three questions. You will see that the second and the third question are a little bit more involved, so take your time. You can answer them during the discussions here. And while you answer the questions, so I can inform you, because you don't know what the questions are yet. And it's also a little bit surprise. So the first question is about what is the most significant challenge in this research area that we encounter now. And yeah, maybe before we see the answers of the audience, we can make a very quick round. So just say a few sentences, what you would say are the main showstoppers, what are the main challenges that you encounter in your research currently. And I will start with this side, and then you can pass the microphone.
Okay, I can answer it with one word, complexity. So, complexity of an amount of the channels and receivers, transceivers, and so on. This complexity we are not ready for, I suppose.
Okay, I think I highlighted many still problems that we affront. Well, also complexity, but I think just dealing with these errors for us is difficult, and getting coding schemes to work with it and scale it.
I think my answer kind of connects to the two things you just answered. I would say the interdisciplinary nature, because we have complexity not just in one area. We're not just talking about coding, we're not just talking about medicine, we're not just talking about biology, we're talking about many different things, and we have to bring all these very complex topics together in interdisciplinary work. And I think that's something we're struggling with, but we see a lot of progress over the past years.
I would also add, and I agree with everything they said. Yeah, definitely. And I think a great challenge is to develop a common language. And it's probably also part of the solution. It's a highly interdisciplinary topic. We have to learn a lot from our side and also our collaborators. I have plenty of collaborators from life sciences, and some collaborations work better than others because people they put more effort in a common understanding than others. And one challenge that I just want, this is probably a little bit more, it's narrower, but it's there, is that many times I go to scientists, they have their own goals, and I have my own goals, and it's difficult to find a common goal. And so when I want an experiment to be done because I want to measure information flow, that is not done easily because the scientist doesn't want to measure information flow, but wants, for example, to find a cure for a disease. And so then we have to find a common ground, and that is really challenging for me, and has been sometimes the stopper of some of the projects I was working on. In one case, I had to give up the collaboration because it was just not working, and so yeah, that's it.
Okay, thank you very much. I think this are all great answers. So let's see what the audience thinks about that. Let me try to show you the result. Aha. Okay. Unfortunately, this one here is somehow. Aha. Okay, so you don't know the answers. A, B, C, D. E. Yeah, I try to show it, but it's okay. So the answers that were predetermined. So I mean, the question was, what is currently the main bottleneck in molecular communication? And the answers were channel modeling A, noise and stochasticity B, experimental reproducibility C, lack of scalable architectures D, missing killer application E. And we can see that we had we have a peak around answer D, but also C and E are chosen quite often. So definitely noise doesn't seem to be a problem at all. But I mean, that's already an interesting observation, because I mean, in our models, when we have the standard communication model, without noise, we would not be employed, no? So nobody, then mutual information would be infinite for some input distributions. So that's already interesting. And then the scalability was mentioned before, so that seems to be a problem for sure. And then the two layers of interdisciplinarity that were mentioned as well. And so I think maybe this corresponds to so that was also mentioned, the killer application. So you have different goals. So for us, maybe the killer application is to understand the information flow, maybe also in the brain. I mean, that would be really cool. And for others, it's to fight a disease. Yeah. So I agree. The killer application is also one thing. I don't think it's missing, but it's interdisciplinary. Yes, please. We'll have another round now.
I just wanted to say the D, lack of scalable architectures. I mean, that's directly connected to the high interdisciplinarity, because you cannot have one model or one framework fits all in molecular communication. It's true also in other communication discipline, but here particularly. And you cannot have your nice additive white Gaussian noise. And noise also comes into this, right? From diffusion, we deal with Poissonian noise, which is kind of similar to what happens in optical communication with the photodetector, but then it's not applicable to all the molecular communication. We have different type of noises at different layers too. So there are different layers of complexity. Just talking about brain, for example, what is the noise there? Yeah, it's not only the synaptic, but it's a lot of other things. So, yeah. So I think it's connected to what we were saying.
Yeah. So maybe we can do another round now.
Yeah.
You know the results.
Should we go this direction?
Yeah.
Maybe you have also some feedback to the audience.
Um,
Because not all, some are working on molecular, but some others not.
I agree with the results. I agree with what Massimiliano just said. And I actually think that noise and stochasticity could become more of a problem with more and bigger models. Because then we will actually see how can we apply those codes? How can we apply communication protocols, which right now we're looking at very simplified versions of what we would like to do in the human circulatory system, for example, and then adding like the real world on top of that, I think is going to lead to a big increase in all the complexity we see here.
So yeah, I also agree with the output. I probably, if I had to choose one, would also not have chosen B, but B somehow is still important to the area I work in. So the noise that comes in is basically why we want to do channel coding or coding theory and work with error correcting codes. But yeah, all the other topics are, if you had to choose one, probably I would also have gone for this. But yeah, I think understanding the noise and the stochasticity is at the theoretical level still important.
So due to my experience, and expertise, I would land in the group C by the reproducibility. For sure, because as I told, our paper, it's 3 years under revision, and mutations. And the Ito-san from the Japan, he generated 7, so they are cell culture institute, and they have generated from the same batch the cells which are adapted to grow in the petri dish for the certain experiment, and they have developed the concrete protocol and distributed into the 7 labs, which only one task was to repeat this protocol with these cells, nothing else. And guess what? Results were all different. So I'm in reproducibility.
Yeah, maybe we can stick to that topic, the reproducibility and the experimental environment, because also from many new topics that are coming up at the future. So many new topics that we discuss here, also the quantum communication and the quantum information theory, molecular. I mean, these topics are difficult, challenging, interdisciplinary, but I guess we can guess a lot of new insights if we really perform experiments. So I would like to stick to that topic and ask you, I mean, you have already started now explaining your experiences with in this case, publishing and presenting experimental results. So what about the other colleagues? So I'm also interested in the DNA. Is it possible to perform these experiments on real? Yeah, maybe you can comment on that.
Yeah, so we are working also with groups that actually do this, that have a lab that synthesize and sequence DNA. And we had also the possibility to visit their lab. So they actually do this, and it is possible to do so. Of course, it takes the time that it takes, and I'm not completely aware of all the steps, but yeah, it is possible.
What about publications? Have you joined publications yet with those groups?
Yes, but that was a bit less on the actual storing on a DNA part, but other topics.
Yeah, I think we, on our side with TU Berlin and Charité, we got really lucky because we're working with the biofluidics lab there, and because they're also engineers, they kind of understood what we're going for. And this search for a common language was a bit easier for us, I think, due to that. But generally, again, like we too were struggling with how do we reproduce this? How do we make it available for other groups who might not be able to research with, like in our case, we're researching blood flow. That's something we can do at Charité, but it's not something that other molecular communication groups coming from the communication background can do. So that's something that I definitely see as a problem for experimental research, because you can't do it everywhere.
And I would add that as communication engineer, we might have to get some experimental dexterity and also tools. It's difficult because they are expensive and time consuming, but our colleagues working on radio communications, many of them, they have antenna labs, for example. So why cannot we have our biolabs? And this is something I have a personal battle in here. Because in the United States, when I was hired and I started my tenure track, there was no biolab for me available, while my colleague in biology or chemistry had one included in their hiring package. So then after being hired, I asked for the lab, and they told me, no, I mean, that there is no money allocated for computer engineers to have a wet lab, and right now I am going on in this battle because I really need a wet lab to do my own experiment on information flow. There are experiments that my colleague in biology are probably not directly interested in. I have more capability now because I was with other colleagues in wet lab. I learned synthetic biological techniques. I learned pipetting and other experimental protocols. But still, my administrators are a little bit blind in that, and I don't know. Probably you have the same problems here. And without, the problem in US at least is that without a wet lab, I don't have access to experimental funding, because I cannot claim I have a wet lab and I can have a project that has an experimental component. So I always have to go in and knock on the doors of my chemistry or biochemist colleague. But that is a problem. As we said, they have different goals, and so I cannot have a grant proposal that talks about measuring information flow. I had to have a grant proposal that says I measure information flow in this big picture of a disease or biodiscovery, which is not engineering, and so then there are a lot of problems there.
Yeah, I think I was going to say that we in Germany with this DFG focus program, we are working on this. But then when I think more about it, I would say it will not solve your problems, because in the focus program, the call is directly targeted to a team, a tandem of one communication person and one life scientist or biology or chemistry person. So in this case, again, they foresee that the lab of the partner institute will be used by the communication people. So I guess this is not, so I understand the problem and it should be addressed somehow, but it's not yet addressed. And if I look at the BMFTR, so Ministry for Research, Technology and Space, programs, molecular communication is only treated as a, let's say, esoteric small side dish. So we are approaching lunch. No? So therefore, I think there's still room to improve.
I mean, just to add to that, in US, molecular communication is not considered at all. So I cannot have NSF, for example, National Science Foundation proposal about molecular communication. That's not a topic. Okay. Yeah.
Then we are doing better. So
yeah, we definitely here you're doing better.
I just want to mention shortly, I have a solution from TU Braunschweig, our own local recipe. You connect to microtechnologists, and they are very open-minded people. And they can translate for you a lot of practical things, because they have always hands-on experience and usually experience in a lot of MEMS, sensors, material science, complexity. So they translate good. And also, usually they are nice people. In our society, in our societies, so as I know, in some conferences they are boring, and in microtechnology conferences we always have a party at each conference, and we very well interconnected, and if you come there you can get the labs for usage also and a lot of help. So connect to microtechnologists.
So I think the audience should also have a chance to ask questions. Okay, yeah.
Okay, so please do not take this in any way personally, because all of you are interdisciplinary and working with specialists. But I have the feeling in our field of communications engineering, we tend to believe we understand everything and can do everything. So what are your thoughts on this? I mean, we have just heard from an expert that we barely understand how the brain works, and 15 years ago I read information theory papers trying to explain how a neuron transfers information. So I'll leave this open to see what you have to say to this. Thanks.
Yeah, thank you. There was another DFG focus program on that. Who wants to answer?
Okay, then I'll start this time. I agree. Just generally, I agree. We tend to think that we know too much, for sure. I sometimes see it with my colleagues. I sometimes see it with myself, I have to admit. And I actually believe that this interdisciplinary work and listening to people from life sciences, listening to people from biology, from chemistry, from microtechnology, that's extremely important for us to see that what we might be believing, we can just solve very easily. That's a very abstract view. And that what we might think is a solution might actually not be a solution. So my answer is, I think interdisciplinary work is the solution.
I actually think if it is so much interdisciplinary, we probably don't know enough, because I miss a lot of the steps from chemistry, but we tend to focus on the parts that we know, and that probably makes it believe that we think we know everything about it, but just because we focus on that specific part that we do know actually. But especially in the thing that I presented, there is so much that I don't understand, that I don't know. So it is important, as you said, to talk to each other and to see what every one of us is doing.
So just to conclude, I totally agree with you that first you have to admire that you don't know. First you have to be honest with yourself and say, okay, I don't know. This experience I gained this autumn with Eduard. We were writing the project together, and I was the bravest one, and I thought, okay, now I will write for immunologists, for Eduard, for communication theory, for myself, for sensors, and for microelectronics as well. And we did not submit this project because the message here is, okay, I could have the interdisciplinary imagination about what is going on, and then the rest, you come to a specialist and he will fulfill exactly this part which he knows. So it's very well that there are parts which we really know, thanks God, otherwise we would be totally lost. And there are parts which we, honest to ourselves, we don't know. And we search for a specialist.
And yes, I think we are trying to solve problems that are sometimes bigger than us. But I want to say this: the one thing that I really like about this research direction in communication is that I can learn a lot. And so I try to be humble, and I try to say, I don't know many of the things I'm working with. I don't know them from the life science perspective, but I try to gain some knowledge. I mean, it's the same process that we use when we started radio communication. I think we learn from physicists and then we learn the Maxwell equation, and then we derive our we adapt it to the telegrapher's equation, and then we started designing radio communication systems. And I think probably now it's much more complex and much more diverse, but I think this is an opportunity for communication engineering to move to the next phase, which is being very useful in many other fields. And I know some years ago, probably people started to think telecommunication was going to be dead, right? I remember when I graduated from my master's, there was no job. That's why I did my PhD. No, it's okay. No, but no, it's not because of that. But I remember there were a lot of companies bankrupting in telecommunication, and because we all solved all the problems of the cellular network, and at that time there was no idea of quantum even. But I think that the next phase of communication is really moving into these other fields, learn, have more collaborators, and use our framework to help others solve problems. So I think there is no bad in that, and it's probably a process that we already went through in other subdisciplines. So.
Okay, thank you very much. Let's see if we are somehow close to a practical molecular communication system. So the question that we asked was, on a scale from 1 to 10, how close are we to a practical molecular communication system? And okay, yeah, it's interesting empirical distribution. The peak is at 3. I think 3 is not very large, so it shows that this topic is starting. I think if you sum up the lowest 3 numbers, we are at 60% of the people. So we have 60% of the people who said that, okay, we are at most at level 3, right? But I understand that this is not an issue, because, I mean, this is the way is the goal, so the way is to do the nice interdisciplinary work, and therefore you will continue to work on that. The good thing is, I mean, there's at least 5% think that we are already at 8. Maybe there are specific applications already where we are at level 8 when it comes to maybe sensor, biosensor stuff. I don't know. Maybe the audience want to comment on that? Okay. I don't see that. So then let's move on to the next final question that we had. And this was a free text answer. So usually I do this with the students in the beginning of the lecture to understand what they think they will learn and match with what I teach. Oh, but it's not a word cloud. I thought, what a pity. So it should be a word cloud with the most often words large. So data storage, that was mentioned, diseases. I hope it will be used to cure diseases. Experimental test beds for research. It's difficult to predict, limited medical application, medical treatments and DNA protein-based data storage, nano robots. No idea, remains unclear, storage, targeted drug delivery, agriculture, biomedical, nanomedicine. And I would like to conclude the session by, again, 1 or 2 sentences, what you think is molecular communication primarily used for in 2035. And now we start with you.
Oh, okay. I would say using biology and biochemistry, engineering biology and biochemistry applications in as many fields as possible, which might include food, nutrition, biomedicine, and all others. But it's mainly getting the tools to be able to engineer biology and biochemistry.
I think in about 10 years, well, almost 10 years, we will be at a point where we will use molecular communication for channel sensing. So the whole sensing part, localization, using infrastructure that is already there. So using this in medical applications or agricultural applications, I think we might be at a stage where we use it for communication in test beds, but not in real life.
So I must admit, I mainly know about the storage part. This is already somewhat possible. So I believe also from working with colleagues, for example, that I mentioned in Zurich, I can see that it works, probably not for a personal use, but like companies or anything. So that does already work, maybe not in the extent that we want. So I can see that this is definitely possible. And hearing from the talks of you guys in the morning also, I think using it, the structure for medical applications seems reasonable to me.
2035 is very soon. So for me, it looks like tomorrow already. I suppose time runs so fast. I hope we could deploy it in the pharma industry. At least what points out the diseases for me, how I can interpret that we can treat more diseases, same as cancer now is going much better with immune therapies. It's still under development, but the promise is there, and 10 years ago it was not available yet. And we did such a milestone. Also in Germany there are treatments. There are improvements still, but this is a hope. And in 10 years, maybe we will do an even more bigger step in the immune therapies against cancer. And I dream about those mitochondrial drugs, which also cure the mental diseases.
Yeah, thank you very much. I think this is a great last statement. We would like to thank the panelists and the audience for the interesting discussions.